immerger is לשקוע. סומרג'ה זה למלא מים, משהו כזה. להציף במים. So I guess that what my remark was incorrect. Those words threw me. Okay. Now. So now forget the field of definition K. What I'm saying now is to, in general, V is an algebraic variety. So unless otherwise said, an algebraic variety is defined a priori over some algebraic closed field, and I'm identified with the points over that algebraic closed field. So given x in V, we define OX to be basically the localization at X. If V is irreducible, this definition makes sense. So I'm assuming again I'm reminding things that you do know. So if you don't, then just read the basic definitions here somewhere. So if V is irreducible, then you can look at the ring of regular functions on V, and you have the ideal of functions or polynomials vanishing at X, and this is a maximal ideal, and prime, and we can localize by that one, and this is OX. Equivalently, and this definition makes sense even if V is not irreducible, I can just define OX to be the ring of germs of regular functions. At X. So again, a regular function at a neighborhood of X is a neighborhood of X, and a fine neighborhood of X, say, and a function defined on that neighborhood. And a germ of functions is the equivalence relation between those, and I identify two if they agree on some, on the intersection of, well, on some neighborhood of X, deeper than the neighborhoods of definitions. And so this guy becomes a ring, which is called the local ring at X, and Mx inside OX is the ideal of functions germs of size vanishing at X. Basically the same definition that we used before, except now we're dealing with regular functions, not analytic functions, algebraic varieties, and the neighborhoods of us are the risky neighborhood. Neighborhoods for the domestic problem, vanishing at X. This is the unique maximal idea. I'll assume we really understand this, unless otherwise said. We defined as before, or formally as before, the cotangent binder, the cotangent space at X to be this vector space over tangent vector at x. X is said to be non-singular, sometimes called simple. Now there are several equivalent definitions, and again, I'm not giving a crash course on that. I'm just reminding you, if the dimension of that guy equals the dimension of phi. I mean, those two dimensions are defined over different fields, right? This is the cool dimension, to be precise. We always have one side inequality here. Equivalently, this is equivalently, I would say that x is non-singular if this is a regular local ring, for those who know the definition of that one. The number of generators for that ring is the same as this dimension. Now, fact, which is very basic. X is non-singular. It can only if we agree that the same condition that we've seen in the end of last hour to exist and find neighborhood x of u of x. Subvariety of an, which is isomorphic to an open subset of V. Such that the ideal, this is the ideal of functions, polynomials, vanishing at u. Now I'm identifying u with the variety, closed variety of an. So I have the polynomials that do vanish on this guy, and this form an ideal, and so this is generated by our polynomials, and the rank of the fx, this matrix that we form, is R. And R here is n minus dx. So basically, again, if you remember the situation we had at the last hour, we had on Kn, we had various analytic functions by then. Now we think of polynomials, and we look at the zero locus of those polynomials, and we assume some non-singularity of the differential of those at a point, then this defines.
X is V, right?
Sorry?
The dimension of V. There is no big X.
Thanks. And the zero locus, of course, is a variety, and is an affine variety. And if you have this non-singularity, we will say that that point, and of course every point in a neighborhood of it, there is a neighborhood of it, because we are talking about vanishing of polynomials or determinant of things, if the determinant is not singular. Oh, sorry. Whatever. Get the point?
You assume here that F is algebraically closed? Or
so far, as I said, I didn't. This is yeah. I did assume that I'm talking over a field of algebraically closed field, but now exactly I wanted to make this remark. If V is defined over a field K, this can be done over K. So X is non-singular. This is the non-singularity of X, or for points X in K. The non-singularity of a point is not defined over a field a priori. I mean, it's some geometric condition, which is, oh, whatever, algebraic condition. I don't care. I don't even want to think about this equation, and it is equivalent to the existence of such an expression if my manifold, my variety, is defined over a certain field K, not necessarily algebraically closed, and if I am dealing with a K point, a point defined over K, this means, for example, that UK here, I can view in KNK, just another way to say Kn. Then everything is like in Kn, and those function here. So what I mean here, the Fi's could be taken in polynomial range defined over. So again, those are standard facts, which I assume we know. So first, V is irreducible. Then the set of non-singular points is risky, open and dense. And the fact that it is open is more or less clear. This is again non-vanishing of certain polynomials. One should indeed show that it is dense. And in particular, let me emphasize that it's non-empty. Definition. It means that we smooth if every point is non-singular. Example. Homogeneous variety. If you have an homogeneous variety, maybe G mod H, maybe G is an algebraic group, you have some non-singular points, but all points are alike. So they are all non-singular. Okay, now this theorem, so far the core thing, this theorem is the corollary of the discussion we had so far. Oh, maybe before let me assume now. I'm having complicated regards to value as before. Assume having an irreducible smooth variety, a variety defined over K. Then Vk as a natural structure of an analytic K-manifold. Okay, I didn't finish the statement of the theorem, but this does not require a proof anymore, right? What is a variety? Let's remind ourselves. A variety is a topological space built out of a finite unit, which has a finite cover by a finite neighborhoods. And also it is separable, it satisfies the house of axiom for the Zariski topology. It's not meaning that the Zariski topology is T2, which means that the diagonal is closed in the doublet, right? Remember this. In any case, locally a variety looks like an affine space, and for the affine space, this definition, or this equivalent definition of smoothness, is the same as the condition that we have seen for something to be a subvariety of Kn. And since being also submanifold, since being a manifold is a local condition, we're done. And let's continue the theorem. Okay, you should figure my notation now. The analytic tangent space at every point x is canonically identified with the algebraic tangent space at the point. Usually I will not write those things down. And here I wrote without defining it, but you understand what I mean? This definition of an algebraic tangent space. Previously I had, well, I guess here I should take points as well. Never mind, let me. When I defined it, of course, I could have taken regular functions over K, right? So this makes sense over various fields. And we will continue the definition here.
So this canonical identification is really using the power series expansion.
You may, this will not be canonical anymore if you use local coordinates. You use the definition, maybe I should not. Maybe I should not raise this one.
No, and I understand if
maybe I'll continue writing the theorem there, but let me pause and make the identification before we do this. The thing is that polynomials are, or regular functions are in fact analytic as well, and so this gives me a natural identification. The algebraic, every function which is algebraic, so if you have a germ function which is algebraic, then obviously I can view them as analytic functions. So this gives me a natural mark here, and if a certain function vanishes at x, also if I view it as an analytic function, it vanishes at x. If there is a function I can express as a product of two such, or maybe sum of product of two such, is this square root ideal, then of course I'm having that one as well.
The fact that the quotients are identified, that's the...
Yes, so this is why I'm bothering to write.
Just a completion.
So in any case, so these two, I'm getting that there is a map. I mean, this map here, or maybe this map to this guy, modulo that guy, is defined modulo that guy. So I'm getting this one. Algebraic guy to the analytic guy. And now, maybe the non-trivial claim only is that this map is an isomorphism. Now, I claim that this map is a surjection. This we can see in local coordinates. So I'm not using local coordinates here because I want to make this canonical. But in local coordinates, I mean, well, these are formal power series, but I view them only up to the. I'm looking only at the linear part of them because I do divide by that. So every such I can represent by polynomial actually with those coordinates by polynomial that only have a linear part. So this is surjection. But now under those assumptions, I know that the dimensions are the same. Hence, isomorphism by equality of dimensions. Okay, and this map that I defined here is totally canonical. So this, so I guess that this theorem, I should explain what I mean by natural, but I will not. This is part of what we see here. And I said that I didn't finish writing the theorem. I just proved that the part that I did write. So what I want to also to see is that if f from V to U algebraic morphism between smooth manifolds, smooth varieties, then I'm getting an analytic function, or maybe restricting, or maybe K morphism. I want it to be defined over K. Then looking at what does to points, I'm getting a map from VK to UK is an analytic function. And under this identification, and you should check and realize that what I'm saying makes sense, we may identify the analytic, so I don't need this anymore, and algebraic differentials of A. So I'm getting, again, I'm an algebraic differential on x between tx v to tx u. This is algebraic, and this is the k version. Or somewhere I should probably it. And I'm having now VK. It's not the same thing. This is the tangent, the analytic tangent space of the analytic manifold VK. And I'm getting the analytic x. And I have the natural identification, and this everything is correct. Okay? As it should be.
Is there any problem defining smooth maps rather than analytic maps
You have this Excel structure for free, so I guess you may find who am asking the same questions. I guess you may define smooth maps as well. Well, I'm not sure. I'm not sure that you have the inverse function theorem for a smooth map. I don't know. Okay, now let's now give an example of things. And my examples will come from group theory. So let's look at the map from C star to C star, taking Z to Z squared. This is a homomorphism of algebraic groups, right? It is defined over 6, certainly defined over R. So I can look at the real points. So this is GA, right? The multiplicative group of the field C, GM, and this is GMR. I can restrict the map to the real points. Of course, the image will be contained in the real point of the target group, but it will not be onto. The image of the snap will be something which is not an algebraic variety anymore, or it's not the real point of an algebraic variety. It will be an open, for the real topology, subset, submanifold of that one. And it will be a subgroup of finite index. open and closed. Let me give you another example. Like, let's take GL and C. Let's take, now I want to look at the variety consisting of all non-singular symmetric bilinear forms of dimension n. Let's look at it over C. So I know that I can, every two are conjugated. I mean, GL and C actually by changing the coordinates. So it acts by similarity, we call it. Act on V by taking A, beta minus 4 goes to G, G transpose. If I think about of A as a matrix. Thanks. Thanks for smiling. And as I said, all the bilinear forms are equivalent, so this is just one orbit. And so V, let me emphasize the point here. VC is GL and C. I can identify with GL and C over all ends. Now I want to look at I want to consider the action of G and R. Or maybe before this, just a minute. We don't get to define here. We continue here. What is VR?
So can you repeat what's ON?
ON is the stabilizer in GL and of standard bilinear form. The bilinear form, which in matrix form is given by the identity matrix. So what is VR? I'm not proving things, I'm illustrating things here. So how many connected components will I have here? Yes, sir.
Either n or n minus 1, depends if you know how to count.
Oh yeah, or maybe n plus 1. So this
goes to show you.
okay, maybe for this, maybe let me consider the action of GL and R on VR. And okay, so here, what am I looking at actually? I'm looking at in matrix forms. I want matrix defined over R, which are symmetric and non-singular, so they are invertible, and they define the bilinear forms. And the bilinear form will have one numerating variant called signature. So it will have, since I is not in R, the square root of -1, then I cannot conjugate every bilinear form to every bilinear form, and I will have problems with minuses, and then I can conjugate everything to something of that form, with so many ones and so many -1s, maybe P and Q. So this is a P comma Q signature form. So maybe the best will be to view it as, I mean, what will the stabilizer of this in G and R? It's the group we called OPQ. And the orbit of this guy, all forms conjugated under the GMN R to this guy is that thing, and this is then. So this is my second example. So again, this guy is one irreducible complex variety, actually homogeneous over the complex numbers, but over the rings it is not homogeneous anymore. We have finitely many components. Each component is a manifold. It's open and closed subset. Now, what I want to say, where I'm heading for a while now, and I introduced all this analytic geometry, etc., for that, is to say that this is the general phenomena. And you might get the wrong impression, just looking at those examples. It might be a little more ugly than that, especially if you go to a positive characteristic. Now, next example, take FPT. So this is K is the field of Laurent polynomials in one variable T over a finite field. This is again a local field, as previous example that we consider. And now take this map, GA, and take X goes to X to the power of P. We know that this is a homomorphism of the additive group. Actually, this is an automorphism of the field. Or it is an automorphism of an algebraic closed field. This guy. It's not necessarily automorphism of FPT itself. It's an endomorphism. The inverse is not. Well, yeah. Yeah, let's exactly talk about interpretability, please. What will be the image of the K point? Okay. So obviously it will be contained.
What is K now?
FPT. Oh. It will be contained here, but it will not be everything. It will be exactly those polynomials or formal power series which are can be presented as formal power series in the variable t to the p. So this in that. This is I claim this is a closed subgroup. Do you see it is closed? So we should recall the topology. I mean, if I have something in a complement, I want to say that if I have a formal power series, which not all non-vanishing coefficient, I mean, which has terms which are not just t to a power of p, then I claim that I have a neighborhood of it with the same property as well. Because how do you define neighborhood? How do you define a nearby guy? A nearby guy would be something which I just add to my guy t to a very high power, right? Or if you want a formal power series which just start very, very late. So if it starts later than my non-zero bad coefficient, then it will not change the fact that I'm not here. Okay. So this is I just illustrate. I explained the fact that this guy is the complement of this is open, so this guy is closed in here. This of course is a closed subgroup. It's the image of a homomorphism under group. So if I let this group act on that variety, so
The topology coming from the matrix.
So when I say I'm addressing topological terms, I'm always regarding the topology, the K topology. I will either say the risky topology
Okay.
or the K topology. So this guy has a K topology, and it's topology coming from the absolute value that I have on here. Did I explain the absolute value here in the examples I gave? So this is a closed, but it is not open. And if I let that group act on that variety via this embedding, I will have infinitely many, and the space of orbits will be very big. The space of orbits so FP.
By that you mean that the quotient is infinite?
Yes. It's not fine, it's infinite. So it has some natural topology because it's a cosine space. It's a group. It's a cosine space of a topological group. This is a locally compact group by a closed subgroup. This is a nice group, but certainly not finite as in these cases. But all those examples, even in post-patternistic, maybe share some common features. Sure what to say first. Maybe I'll say something, some teaser for later developments. We'll see in the future. There's a theorem by Borel and Serre. This works over a local field, Archimedean or not, but of characteristic 0 only. G acts on V, homogeneous action. Defined over K. Then when GK has finitely many orbits in VK, all are open and closed. Actually, the fact that they are all open and closed, we'll see today, I hope. So, for that, we will develop a tool called Galois homology. So, who saw some Galois homology before? That's a lot. But not today. So today we see much less than that. But our setting will be much more general, and as this example shows, we cannot generalize that Borel-Stella theorem to general local fields. We see today, I hope, G acts on the homogeneous, etc. Then every orbit of GK in VK is locally closed. So is this term familiar? So I thought I'd better, I don't know if this is necessary, but I assume it won't harm if I'll give some introduction to. I'll redefine for you what locally closed means and what constructible set is in topological space. Okay. So again, I'm recalling things I assume you know. And now, for a minute, I'm leaving analytic geometry. I'm leaving algebraic geometry behind my back, and I'm defining that X is a topological space. Maybe I will use this house now. I'm not sure. So the set in X is locally closed, or maybe I'll give an equivalent definition, equivalent condition. For A in X, a set, the following are equivalent. A is the intersection of an open and a closed set. And which is the simplest form. And the next is maybe the origin of the term locally closed. I want A to be, well, locally closed. So here's the definition of it coming. For every A in A, there is a neighborhood of it in which A is closed. So for every A in A, there is open neighborhood such that in that neighborhood A is closed with respect to the induced topology. But let me underline this for you. That is, I'm underlining the definition. Exists FA in S closed such that that guy these are closed sets in UA, right? 3 and it's an exercise for you to move between 2 to simplification 2 to 3. So every point as a neighborhood, such that the claim is that I can take this FA always to be the closure of A in X. Okay, so this is 2 to 3 is not completely trivial, maybe. maybe use autofluence here, I'm not sure. But I leave it to you to check. And 3 implies 1, how? Well, so what will be F that you take? A closure, of course, and what will be U?
Yes.
The union of all the UX. And okay, so probably again put on the board, def locally closed. So set as above, hold locally closed. Now here's another definition. A constructible set in X this A is a non-definite particle. So it's not a set. A constructible set in X is a set in the Boolean algebra generated by the topology. So I want open sets to be constructible, I want closed set to be constructible, I want their intersection, that is locally closed set to be constructible, I want finite union of such to be constructible, and in fact, a claim, easy claim, finite union of locally closed. So check intersection of such is against such, finite union of such is against such, complement of such is against such. Okay. Next, I wanted to bring some very basic exercises about these notions, because I'm actually, to some extent, I'm not to use it without even mentioning, so I want to know. And some of this is not completely standard. 4. A in X, we said U of A will be kind of the locally closed biggest chunk of it. So it will be all the A's in A such that A is locally closed at the neighborhood of A. A in A such that industrial writing, Kayam exists, open neighborhood, and this closing such that at this neighborhood A is closed. And we set A1 to be the complement. And we set AN to be AN minus 1, 1. So if a set is locally closed, then it is locally closed at every point of it. So A is UA
So you can. I'm asking regarding. I'm just making sure I understood the definition because here you define locally closed, not locally closed as a
Yes,
point.
yes. So a set. So I think this is 2 here, saying that a set A is locally closed if it is locally closed at every point.
The question was, is this the definition of locally closed at every point? Is this a defining equality?
So
Yes. This is explaining what this is. Just in the future, I will not rewrite this. Let's make some observations. So U of UA is U of A. And U of A is A. From these two, from QA is always looking close, right? And if for some n n vanishes, then what? Then n is constructible. Because then A is the union of the U's of the. Then A is the finite union of the U's of the K. Which are all operators. And so here is a lemma which I'm not doing.
can you give an example?
Yeah, I
Give
should.
a picture.
Yes, here's an example. 0, 1, the interval 0, 1 in the plane. Maybe I should, yeah. So it's the intersection of that string with that line. Also, every point in it has a neighborhood in R2. And if I restrict to this neighborhood, my set A is actually closed.
So what would be A prime? So no, this is a local closed.
If it's locally closed,
But what about the situation where this A to the power of 3 is vanishes for the first time?
let's take it. So half open interval. What will be A prime?
Zero.
Hmm?
Zero.
No.
The open interval.
With the open interval, and only afterwards it will be 0.
So A1 would be A minus U of A is the set.
It's those points for
UA,
which I can find a neighborhood.
That's UA. UA is the open interval.
So,
UA is the open interval.
Is the
Sorry?
UA is the open interval.
Yeah, I guess it's locally close as well. That was stupid. So yeah, so this is the intersection of, I don't know, that half space with that ray. Let's say, I guess I should, I don't know, maybe take this with half of its boundary or something like that. And think about it. I guess now we'll have some problem at the meeting point. I mean, here take the boundary, here don't. And something will stay if you take the first prime. Okay, you should think about it. But nothing here is very hard. But actually, this lemma is not triviality. I leave it for you. This is an exercise. The exercise is to prove that this is if and only if. Again, this is just, it's something that you can give to your students in the first week of topology. There is no sophistication here. But it's not complete reality to do it. So A is constructible, near don't.
What was he going to do?
I'm not teaching
You're not teaching? Okay.
He's teaching.
I mean, the second or the third will be fine. No. So it's if and only if here. Two is basically this remark. It follows immediately. Three follows. So just let me explain the third one. So you agree that for every k, ak plus 1 is a subset of ak. So it follows that u of it is a subset of u of ak. And by induction, it's a subset of u of a. So all the u's are subset of u of a.
So A is the empty set.
No,
So you
No.
close the union is
no, you don't have that u of k plus 1 is in u of ak. ak plus 1 is the...
Yeah. Okay. I'll. Yeah. U is not a monotone operation, and okay. So yeah, it's two lines which are written wrongly in my notes, so I cannot do it. I mean, probably I can, but I won't do it now. So you put this as well. So and I don't want to waste more time on those things. So you can do it over T and case now. And with this, I'll come back to algebraic geometry after